Yeah, so basically we have to start with that what you say heat engine, Carnot cycle. Like these are like very important applications of thermodynamics. You can say that we have to do that. We will do that. But before that, like one very important topic we will discuss, like whatever we discussed uh, on entropy, we will summarize it. Like
Yes.
entropy change during different processes that we will discuss. Entropy change during different processes. Like we have so many different type of processes: isothermal, adiabatic. So in different processes, what will be the change in entropy that will be entropy change during different processes. This is a very important discussion which we will be making. Entropy change during different processes. So the first, yeah, the first scenario which we will be discussing, that is when we have the variable temperature and volume.
Yes.
First scenario, we have an ideal gas. We have an ideal gas. In the process, ideal gas is involved. In the process, ideal gas is involved. 1 mole of ideal gas is involved. And we have variable, like with varying variable temperature and volume. A process with variable temperature and volume, ideal gas, 1 mole of ideal gas is involved, then what will be the entropy change? That is what we are discussing. So for such processes, delta S, the change in entropy, it will be equal to CV log of TF by Ti, because variable temperature will, so temperature will change with time, plus the universal gas constant R log of Vf by Vi. So this is the entropy change. Now let us look at the second process. We have an ideal gas, the same 1 mole. 1 mole of ideal gas. And now in this process, pressure and temperature is variable. With variable pressure and temperature. Here, once again, the change in entropy, which is the delta S, it will be Cp log of Tf by Ti, like final temperature upon initial temperature. Log of let me write it down. Log of Tf by Ti plus okay, here it will be minus universal gas constant R, universal gas constant R, log of Pf by Pi, log of Pf by Pi. Pf by Pf. So this is the second process. Now we have the third process. Now we have the third process. For an ideal gas, one mole. Okay, so here we can say that for okay, one mole let it be. For an ideal gas, one mole in an isothermal process. The process is isothermal. Isothermal process. And we know that isothermal process is constant temperature. Constant temperature. So when we have the temperature constant and ideal gas is involved, so what will be the change in entropy? Let us look at that. So the change in entropy delta S, it will be equal to universal gas constant R log of Vf by Vi, final volume upon initial volume. and it will be further equal to minus R log of Pf by P. Like if pressure is given, then we can use this formula, and if volume is given, we can use the other formula. But and we call it delta S with the subscript T. Here T denotes the constant temperature. So in an isothermal process, change in entropy, it is dependent on the universal gas constant and either the volume or the pressure. But temperature is constant. And all this you can derive with a basic formula that delta S is equal to delta Q by capital T. And now the fourth we will do, because now we are interested only in the results.
Yes, sir.
Fourth process. We have an ideal gas. For an ideal gas, uh, in isobaric process. In an isobaric process. And we know that isobaric is pressure constant.
Pressure was.
So we have a process on an ideal gas in which the pressure is constant. And the change in entropy, we have to check. Pressure constant or constant pressure. The change in entropy will be, we can call it delta SP. Change in entropy for an isobaric process. It will be Cp, molar heat capacity, like heat capacity of 1 mole of ideal gas at constant pressure. That is Cp log Tf by Ti, because here temperature will change. Tf by Ti. And the last process which we have to look into, that is the isoporic process. Fifth process is the one wherein we have an ideal gas for an ideal gas in an isoporic process. Volume, constant volume. Isoporic process means constant volume. So we have something like this. Change in entropy, we can represent it with delta S with the V subscript. It will be molar heat capacity at constant volume log of Tf by Ti. Where Tf is the final temperature, Ti is the initial temperature. So now we looked into the change in entropy for different processes. So entropy change during different processes. So this is clear to us.
Yes.
And yeah, so these results are like very important. Now we can straight away jump into the heat engine. So first let us get some idea about heat engine. Then our main focus is the Carnot cycle. So let us look at heat engine. This heat engine was a part of industrial revolution. Like if we talk about industrial revolution, we have seen three types of industrial revolution. So first was the mechanics. Second was the thermodynamics, because of which thermal engines, heat engines we were able to make. And the third was the electricity, electromagnetism. And now the fourth that we are calling it as industrial IoT, industry 4.0. It is the data, automation, intelligence. So heat engine. So heat, like this thermodynamics played a very important role in the industrial revolution. Now let us try to understand what is this heat engine is about. So if we talk about heat engine, it is basically a device which can convert the heat energy into some mechanical work. So heat engine is a device which basically converts the heat into work. Because in all like industries, machines are running, and all the machines they are doing some kind of a process, some kind of a processing those machines are doing. Now we have to run that machine. So in order to run that machine, energy is needed. So thermal engine, it needs heat energy to do some kind of a process, to do some kind of a work. Now we have uh, like we call it like the uh, engine powered by the electricity, or machines powered by the electricity, like motors. But earlier, these heat engines were very popular, and now still we are using heat engine for our vehicles, automobile. In automobile, it's all about heat engine on, wherein we burn the fuel to generate massive heat energy, and that heat energy it drives the piston, like some mechanism to drive the vehicle. And this transformation, it's a cyclic process, very important. heat engine follows a cyclic process. Cyclic process. Now, how this heat engine works, this cyclic process, two components are involved. One is the high temperature, another is the low temperature. Because we know that heat energy always follows from high temperature to low temperature. So let us suppose I have a hot reservoir. And I have a cold reservoir. Now this hot reservoir, I can say something like this. It is having heat energy 2H. And I have a cold reservoir which is having energy QC. At any point of time, the difference in the energy is the one which will try to transfer. Like very important observation we are making. Whenever there is a difference in the energy, like if,
Yes.
then heat will flow. Heat will flow. Delta Q. QH minus QC. Whenever this delta Q is a positive number, heat will flow. And heat can flow in both the direction. It is not, it depends on delta Q. If delta Q is negative, then it will flow in the other direction. And delta Q negative means cold reservoir, it became hot. And hot reservoir, it became cold. In that case, this formula, let me write it properly. This I can shift to. This is the formula. Now, two conditions arise. Two conditions arise. If delta Q is positive, then the direction of flow will be from hot reservoir to cold reservoir, according to the formula. But if delta Q somehow it becomes negative, it means that the cold reservoir it becomes hot. Then it will flow in the opposite direction. Hence, it is a cyclic process. Why it's a cyclic process? Because after some time, when the heat will be supplied from the hot reservoir to cold reservoir, hot reservoir will start becoming cold, and cold reservoir will start becoming hot. The heat transfer will take place in the other direction. But we never want that, because if that is happening, then the mechanical work we will not be able to derive. And for that, what we have to do, we have to keep the hot reservoir hot always. And for that, we burn the fuel. In order to keep the hot reservoir hot, we burn the fuel or we burn the coal, so that the heat energy constantly we are supplying. And because of that, this reaction or this process will always be in the forward direction. Continuously we are generating the heat energy, and that heat energy is getting converted into the work. And just imagine, with this concept, we were able to invent trains, railway trains powered by steam. So interesting it is.
Yes.
And all the automobile, they follow the same principle. So the main principle behind the heat engine is this: the transfer of heat from a hot object to the cold object. Now we will look at the concept of Carnot, like Carnot cycle.
Carnot, sir, we even studied in 11th. Carnot
Yeah.
engine. It's in some chapter.
Yeah. It is in thermodynamics only, because in 11th
It is
chemistry,
also, I think,
it is in physics also. Yeah, you're right.
physics also, yes.
Yeah, both subjects. And this
I think
signifies
12th,
the
12th,
no
yeah,
12, 11th.
physics. 12th
Physics
physics,
also,
11th chemistry.
no, physics also 11th physics, because this thermal chapter, it was in 11th. In 12th, in physics, you had electromagnetism, optics, and modern physics. In 12th physics, uh, you had no, not that, electromagnetism, optics you had, modern physics you had,
Yes, sir,
right,
yes.
according to the NCRT. Now we will discuss Carnot. And it's been so late in that way that we are moving towards electric vehicles after so long, because electricity is something which was invented so long ago, and we were able to invent machines which has been operated by electricity, but the automobile sector operated by electricity, like electric vehicles, now we have realized that after so long, isn't it? Yeah, it's also strange.
It's a purely business.
Yeah, business, but yeah, like we have to look into the feedback, but yeah, companies are running, it means that we can rely on electric vehicles,
But
although
now we can't.
now we can't now, because I have heard that in terms of performance they are not that much good, they are not
The
powerful.
performance also it's fine, but
Yeah.
uh, after 5 years, you have to get the battery changed,
Uh-huh.
and the cost of the battery is half the price of the vehicle.
Oh,
If you get a car of 10 lakhs, then the battery costs around 5 lakhs and you have to get it changed after 5 years.
oh, so
So
maintenance
it's not
cost
reliable
will be
right
huge.
now.
Oh,
Yes.
okay. Yeah, because in India, the two-wheeler, if they buy it,
Mhm.
they use it for 15-20 years.
Yes, sir.
For 10 years, or aram se they use it. Yeah. Okay. Yes. Yes. So let us look into this Carnot cycle, what it is. And as the name suggests, it is named after a scientist. So it is named after a French scientist. French scientist. That is Sadri Carnot. And he's a French engineer. He's an engineer. He was an engineer. And one very interesting thing you will realize that after 1500, all the major breakthrough in the science, in the field of science that we have seen or that we are studying, that the origin is Europe. like Newton,
Notice this.
Albert Einstein, or all the Maxwell.
Yes.
All of them are
Albert
Europe.
Einstein was from Europe.
Yeah, yeah. He's German, no? And Maxwell, all that. James Clerk, Maxwell. Yeah. All the engineers, like the scientists, very famous scientists, which we study their principles. Like their origin is Europe. So French engineer Sadiq Carnot. So Carnot cycle. So what it is, let us look at it. Carnot cycle basically it's so famous. Why it's famous? Because as the name says, it's a cycle. And what that cycle is, it's a cycle of four stages. It's a cycle of four stages
Yeah.
and four reversible stages. That we will draw. That we will draw. We'll draw the Carnot cycle. So the x-axis, we have the volume. In the y-axis, we have the pressure. Now we can draw 4 points. We can draw another curve. Let me draw the curve. Here accuracy matters a lot. Hmm. Now I can draw the two curves. So we will delete that. Um, like this here. Okay. So curve I will follow. This is the position. Your last correction. This is still not applicable. Raise it. Small correction. Like, something. I can run that so that it will not be a straight line. Delete that. That is okay. Yeah. So let us mention the points A, B, C, D. So the Carnot cycle. So first stage is the A to B. That is the first stage. Second stage is the B to C. Second stage. Third stage is the C to D. The fourth stage is the D to A. So 1, 2, 3, 4. Now the first stage, it signifies the isothermal. Isothermal. Constant temperature. The process, the constant temperature. Second is the, okay, not like this. So the idea is that the blue line which I am having, that is isothermal. The red line I am having, that is the ideal. So let me tell you, this two blue lines I am having. This line, this is isothermal. This blue line is also isothermal. This line which I am having is adiabatic. So this is the Carnot cycle. Now, how to interpret it, how to analyze it, that we will discuss very soon. So now the idea is that we have to do a work. Either work is done by the system or work is done on the system. So the gas, if gas expands, then work is done by the system, and if gas compresses, then work is done on the system. Now, what is our goal? Our goal is the maximum convertibility of heat into work. So the Carnot cycle, it demonstrates that. it's an ideal scenario. In the ideal scenario, we can derive the maximum work out of the heat, and how we can do that we will discuss. So the context is clear to us that we have a system. We have a system in place. Let me write this down. The system which we have, that is basically a 1 mole of an ideal gas. System is basically 1 mole of an ideal gas. What is the and 4 strokes? So 1 mole of an ideal gas subjected to 4 stroke. Very important. Subjected to 4 strokes.
So
In the
these are
system,
the 4 strokes, no?
these are the 4 strokes. And we will discuss all these 4 strokes. So we have an ideal gas subjected to 4 strokes, and this ideal gas, it can either be compressed or expanded. The work. The work can be either the compression work or the expansion. Compressor. And what is so we have a system in place, 1 mole of an ideal gas. Either we can expand it or compress it. This 1 mole of an ideal gas will be subjected to 4 strokes. And what is the objective? Objective is to derive the maximum work. How we will do that? That is what Carnot explained. It is a kind of a theoretical model. Practically, like theoretically, though, it gives us very good result, but practically, this is infeasible. Like whatever he is saying, the performance, the efficiency, that we cannot achieve. Objective is maximum convertibility of work, of heat into work. Maximum convertibility of heat work. That is what is Carnot. Now let us see how we will do this. So 4 stroke, every stroke we will analyze, then we will get a feel of it. What is happening? So you, I think, mute, and if you want to ask anything, please unmute. I think there is a disturbance. So let us first look into the first stroke. What will happen in that? Every stroke we have to analyze. So first, let us look at the first stroke. The first stroke, the graph, let me draw it, copy it constantly. Because every time we will be needing this graph to see the picture, what is happening. P is the pressure. First stroke we know, let me highlight it. This is the first stroke which I have highlighted. So the curve AB, first stroke is the curve AB. Now what it is, so in the first, see, very clear to us that in AB volume is increasing, and if volume is increasing, it is expansion. And the blue curve isothermal is written. It means it's an isothermal expansion. Isothermal expansion is constant temperature expansion. So in the first stroke, what we are trying to achieve, isothermal expansion. It is evident from the graph itself. Isothermal expansion. And let us suppose the constant temperature, let it be TH. And since expansion is taking place, it means that work is done by the system. Work is done by the system, or work is done by the gas. Work done. Now, second stroke we will discuss. Let us be a bit fast. Second stroke. So let us once again get the graph. The graph, we are getting it. So I press the key multiple times. Oh, fine. There is a key for lock. Okay, let it. Just 1 minute. Now let me highlight the second stroke. That is this region. That is the curve BC. Now what it is, let us see. So as it is evident uh, that still in BC also volume is increasing a bit, and hence it's an expansion. But the curve is the adiabatic, so it's an adiabatic expansion. So in the second stroke, we are having the adiabatic expansion. Let me write it. Adiabatic expansion. And since it's an expansion, work is done by the gas. Since it's expansion, work is done by the gas. See, let me write. Now the third stroke. I took copy this one, bad. So let us now do the third stroke. Now we are doing the third stroke. Now this third stroke, let me highlight it. It is C to D. It's the curve CD. Curve CD. In this curve CD, the now see volume is decreasing and the curve is the isothermal. So it is isothermal compression. It is isothermal compression. Isothermal compression. At TC, like temperature, let us take as capital TC. Since it is compression, work is done on the gas. Work done on the gas because it is compression. Now the last fourth stroke, let us discuss. Fourth stroke. It will be the DA. Curve DA. And definitely here it will be a compression, but adiabatic compression. And work done on the gas. It will be a adiabatic compression. Work done on the gas. So these are the four strokes. And Carnot proposed that if these four strokes are applied, then automatically we will achieve a very good efficiency. Magical efficiency we will achieve. Shift to make it more visible. Okay, now it is clear. Like in the one frame it should be visible, no? So that easy to look at the things. Yeah.
Yes.
How it is looking in the one. Okay, so now like today we can keep it till here. Then see now our next goal. Now we got an idea that okay, what is the Carnot cycle? The four strokes. It means that uh, if we are doing a mechanical work, like if we are converting the heat into mechanical work, first we have to do the isothermal expansion, then adiabatic expansion, then isothermal compression, then adiabatic compression. If we do this, then we will achieve the maximum efficiency that we will prove in the next session. We will prove that how is it so.
Yes, sir.
Yeah, just so So we are